Right, so I welcome you to yet another chapter, and in this chapter we're going to be looking at the basic network concepts, and we want to understand some of those few concepts and also to try and grasp a few network concepts. So moving forward to the next slides, we are saying that to understand security technologies, you first need to learn about basic network concepts, such as basic communication principles, network components, and common network protocols. With knowledge of these basic concepts, you can better understand network security threats and also deploy security defense policies. You will understand today that even you who is able to join this meeting, you are using some kind of network device. Either your phone is acting as a router or you're connected to a Wi-Fi somewhere, which is assigning IP addresses to you, and you're using some kind of protocols to receive packets from the class, from Zoom, and also to send back packets if you must communicate back. So it is important for you to understand how the network works, to also understand some of those concepts and the underlying concepts, so that you as a network engineer, it is easy for you to protect the networks, and it's also easy for you to to make sure that you actively keep updating your network security. So upon completion of this course, you'll be able to describe the working principles of TCP IP protocols. I think the network engineers on this call are very, very happy, and you'll be able to describe the working principles of common protocols and also describe the possible security threats to common network protocols. Let us try and look at the TCP IP architecture. And in the common campus network or enterprise network, usually this is a logical kind of organization of a network architecture. And usually you have some of these devices at your enterprise or at your premises. You have your access layer, and on the access layer, this is where your end users are connecting. You have different computers connected here, and you have your, let's say, wireless access points giving Wi-Fi to your end users. You have different people connected to your access points. Now, these switches, this could be either at block A. This is just a logical organization. This switch could be at block B. This switch could be at block C, or even this one could also be, somewhere, let's say block A, or even say first floor, second floor. Not necessarily all these devices are in the same room, but these are switches. And we also have we have our aggregation layer, we have our core layer, and we have our egress layer. As you can see, all these switches are connected to our aggregation layer in redundancy mode. As you can see, there's one link here, there's also another link here, meaning that even if one link is off, we can still, this end user connected here can still go ahead and send packets throughout the internet. And as you can see, we have our core layers, and we have our firewalls, and we have our routers, we have the internet, blah, 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 blah. So in a medium to large networks, modular design is usually used to split our network functions within each module. Consideration must be given to flexibility and scalability of the network. You need to be able to add devices or remove devices at any of your convenience, but not necessarily affecting the hierarchical structure of your network. Traditional networks like this network you're seeing here usually contain the core layer, aggregation layer, and access layer. The core layer usually provides us with high-speed data channels, whereas the aggregation layer here helps us to converge our traffic that is coming from our access layer. And here usually you have our traffic and control policies, and the access layer will offer access, nodes to our end users. So let us look at the OSI model. OSI model. Our network engineers in the call, how many layers are in the OSI model?
4.
7.
7. 7, sir.
Yeah,
7.
7.
Yeah, 7.
Yeah, 7.
7, sir.
7.
Okay.
TCP IP.
7 layers.
There are 7 layers.
All right, I heard that loud and clear. Thank you all. Thank you all. So the OSI model, or what we are calling the open, what we are calling the open system interconnect, forgive my handwriting, reference model is what we are calling the OSI model. The OSI model is designed to overcome the interconnection difficulties and low efficiency issued with various, protocols by defining an open and interconnected network. Before we had the OSI model, every, vendor, every, manufacturer had their own kind of protocols, and there were few by that time, and it could be hard for people to effectively communicate. But right now, you're rest assured, when you send me a packet, I will receive it as long as I'm connected to the internet and I'm well configured on the network, isn't it? Because there is some kind of openness and there's some kind of interconnection and there's some kind of interworking together, and also this reference model, it's going to reform the basis of computer network communications. It is designed basing on some principles, and the principles we're going to look at them. It's designed basing on some principles and also has some advantages. So when they are designing it, they looked at it and they say, we're going to design this model and we give it clear boundaries, right? Clear boundaries between layers to facilitate understanding. That there's going to be a clear boundary between the 7th layer, and there's also going to be a clear boundary between the first layer, or even the 2nd layer, or even the 3rd layer. And we're going to be looking at those layers for the people who have never done networking. So each layer implements specific functions and does not affect the other. Like application layer is going to do its part, the session layer is going to do its part, the presentation layer is going to do its part, and them doing their part is not going to affect another layer. And each layer is a service to a service provider, to a service user, and specifically each layer provides services to its upper layer and uses services provided by its lower layers. For example, the data link layer or the physical access layer will send packets to the data link layer, and also the data link layer can send packets to the physical layer. And the division of the layers is encouraged the development and standardization protocols, and there are sufficient layers to ensure that the functions of each layer do not overlap. When it comes to the advantages of the OSI model, is that the OSI model, because it is designed using on layers, it helps us to simplify network operations. It also helps us to have a standardized interface and also support plug and play devices. You have different vendors, Cisco, Huawei, Lynx, and you can bring those OLX, you can bring those vendors, and you can just plug your another device onto the network, configure it, and you are good to go. And it also enables vendors to design interoperable network devices, because when vendors are designing their devices, they know they're going to use these protocols, and they are going to also make sure that they can be used in any network architecture. So it simplifies network issues and also troubleshooting, because you know that if my device is not getting an IP address, then which layer is that is affected? Let me start troubleshooting from layer 3 and try and see if maybe there's something that I need to check out. So the OSI model, units of data are collectively called the protocol data units, the PDUs, protocol data units, and each PDU is called a different name according to the layer at which it is sent. So if it is sent at the application layer, it will be called the APDU, because it's an application protocol data unit. If it is sent to layer 6, it will be called also the PPDU, the presentation protocol data unit, or the session protocol data unit. However, when it comes to transport layer, Then now at our bottom 4 layers, then now our data will now start to be called a segment. And after that, when it's sent to layer 3, we shall be looking at packets. And then if it's sent to the data link layer, we shall be looking at frames. And if it's sent to the physical layer, then it shall be sent to, it will be called a bit, because now we are looking at a bit stream. So each layer of the OSI model encapsulates data to ensure that data can reach the destination accurately and can be accepted and executed by the terminal host. A node encapsulates the data to be transmitted by using a specific protocol header for transmission. And when the data is processed at the layer, packets are also added to the trail data, which is also called encapsulation. So what happens? We have our 7 layers here. We have our application layer, which is a 7th layer in our OSI model. And here, basically, it is used at the topmost layer that the users face, right? And it provides communications between applications. You are in your Chrome, you're in Zoom right now, and chances are, actually not chances are, you are using the application layer. You're clicking on your mute microphone, speaking back, sending packets here and there, and you are using the application layer, and it is providing communication between applications. My communication here from my Zoom to where you are to the browser, etc. We are using the application layer. But now think about it. You have sent an audio. How is it going to be transmitted over to your Wi-Fi, through the internet, I don't know, through the cloud, to where, and it's going to reach me and I'm going to hear you? How is that even possible? So we have also the presentation layer. The presentation layer helps us to process the data formats and encrypts the data, so that even when it is going over our network, our data is encrypted. And also it's going to process the data format. Is it a picture? Is it an audio file? Is it an XML? Is it an HTML? Let me also encapsulate it accordingly so that it can be sent over the network. Isn't that beautiful? So we have our session layer. Yes, who can be able to send and receive at that given time? We have our session layer, and the session layer here deals with establishing and maintaining and managing sessions. You are connected. Has the session been has the session been established? Have we sent the handshakes and we have really fully established the session? Is it authorized even to access that platform in Zoom? You're going to log in, put your email, put your name, and then say register. It's going to send to to and establish a session. And then after, when the session is connected, then we are happy, and then it will maintain. And after, when you're done, you're tired for some reason, and you'll be like, end meeting, and then you go away, the session layer will be concerned with making sure that that session is closed. But while you're on Zoom, it will also make sure that it will go ahead and it will maintain the session until when you're done doing your communication. So who is getting constant pop-ups? Anyway, I was trying to read your chats there. So we're looking at the transport layer now. We have established our sessions, but now this one establishes the end-to-end connections for our hosts. It's going to make sure that there's end-to-end connections between the host that side and the host on my end. Now we come to the network layer. It performs addressing and routing. All the IP addressing is done at this layer, making sure we have IP addresses, making sure our computers can communicate over the internet, and also routing across different network segments. We also have our data link layer, and the data link layer provides media access and link aggregation management. Here we also look at the media access control, the MAC address, and it basically is going to work at layer 2. Basically, it looks at providing media access, that it can access the media, and also there's also some kind of link management. And we finally look at the physical layer, which just transmits the bit stream. Yeah, cables that are there that are going to just, transmit the bit streams onto our network. Now, the network engineers here, if you could just kindly tell us what devices or what applications work at the application layer?
Firewall.
Application layer?
Browsers.
Firewall.
Mic check.
Go ahead.
Browsers.
PC.
Browsers like Google Chrome.
Browsers like Chrome, email
Firefox.
clients, Zoom, etc. Right?
Yes.
What do we find here at the
Google Meet
physical?
is
What we
also one of
find
them.
here at the physical layer? Also, someone said Skype. Yes. What we find here at the physical
Cables.
layer?
The cables.
Cables. Very good. What else? Someone said Cat6. That is a network cable. Yes.
Switches.
Transformers.
Transform.
Switches. Switches.
Switches, no.
Switches, no.
Fiber optic.
Fiber. Fiber.
Optical fiber.
Okay.
Network
Fibers.
interface card.
That's under cables.
All
The
right.
fiber optic cables.
Someone said the network interface card.
What is the optical fiber cable?
Someone.
What
if you have
about
noise-
radio?
Members, please,
Then
whoever
Daddy,
is
if
in
you
a
have
noisy
noise,
background,
please do
mute
not
yourself,
unmute
please.
yourself. I'm just going to put you in the waiting room. If you know
What
you
is
have
that?
a noise background,
We have-
I'm not going to repeat this again. If you know you have a noisy background, it's like you come into class when you have your friends and you're making noise. Please, just kindly make sure you don't unmute yourself. We don't want to hear your noise in the background.
But
Optical fiber cables.
Okay. All right. Let us look at the data link layer here. What do we look at here? This is layer 2.
Routers.
You sure? At
My-
layer 2?
Switches.
Yes.
Switches.
Switches.
We are looking at switches.
Switches.
Okay.
Routers.
Route?
Switches.
No.
Routers.
Network layers is routers.
We have hubs. Yes.
Hubs.
All right. All right. All right.
Even bridges.
Even bridges. Yes. Okay.
Repeaters.
Even repeaters. Thank you.
Computers.
All right.
What about access point?
How about layer 3?
Routers.
Routers. Very good.
Switches as well.
Layer
Four
3.
switches.
We have layer 3 switches.
Switches.
Layer 3 switches.
Yes, exactly.
Just do that, Mr. Ssendi.
Okay,
What's
so-
the difference between a router and layer 3 switches?
We
How
are,
do they categorize differently?
MiFi.
we are going to look at the common network devices, so you get to know the difference between the switch and the router later on. So don't worry. Don't worry for those who have not done networking before and you're hearing is what, no worries. So let us look at the peer layer communications. We are going to look at how these things are going to be encapsulated and decapsulated. So each layer uses
Mr. Ssendi, just a contribution.
Yes, please.
The one who asked the question between the difference between routers and the layer 3 switches is that layer 3 switches are more intelligent than those that appears at the data link layer because they have routing capabilities. Thank you.
Thank you. Thank you. So each layer, thank you.
Mic check.
Yes, please.
I also want to contribute something. Somebody was talking about MiFis. MiFis are routers. So we consider them as routers.
They are mobile routers.
Yeah, and access
That's the
points.
MiFis. MiFis are mobile routers. Okay, that provide mobile access points.
All right. Thank you. Thank you all for the submissions. Allow me to...
Press continue, sir.
All right.
OPC.
All right. So we want to continue just a moment. Just give me a moment. So we're looking at the peer layer communication, and we are saying that each layer uses the services provided by the lower layer to communicate with the peer layer. The data link layer can send things to, let's say we want to send a packet from host A to host B. The application layer is going to generate it, the APDU, the protocol data unit, is going to send it to the presentation layer for formatting, session layer to establish the session, end-to-end connection. It's going to perform the routing and addressing, and then the data link layer is going to do the media access and link, aggregate management, and then send the bits to the streams of physical medium, and then they'll be shared to this. And this one will receive it, de-encapsulate it, send it to the data link layer, go ahead to the network layer, do the same transport layer, session layer, or that presentation layer until when it is sent and received to our physical hosts. So managing mapping between TCP IP and OSI model. The TCP IP protocol stack has a simple hierarchical design and a clear mapping relationships with the OSI model. What happens that we're going to combine the top three session layers, all the way from application layer, presentation layer, session layer to the application layer. And then we shall have our our transport layer, the same as transport layer, network layer as internet layer, and the data link layer combined together, the physical layer as the network access layer. So the TCP IP model has 1, 2, 3, 4 layers, although some references mention 5 layers of the TCP IP model. So the transfer control protocol, or the IP or the internet protocol, is a model widely used and was used due to its openness and usability. The TCP/IP protocol stack is implemented as a standard protocols, and the TCP model is divided into 4 layers. From the bottom to top, we have the link layer. If some organization which will choose to have the link layer, you have the link layer, and then you have the internet layer, and then you have the transport layer and application layer. So, like I said, some documents have defined it as 5 layers, where the link layer is split into the link layer and the physical layer, equivalent to layer this and that, right? So let us look at functions of each layer from the TCP IP. We have the application layer, and the application layer, we said it provides network interfaces for applications. And these are some of the protocols within the application layers. Maybe just to ask, what is this protocol used for? Anyone? Just a mic check. And the first one to say mic check.
Mic check.
Go ahead.
The hypertext transfer protocol is basically used to transfer content from our computers now to the host computer.
Using what?
The web.
IP address.
This is very, very important. The web, right?
Using www.
Okay. How about telnet? Anyone?
Using SSH.
Mic check.
Yes, please go ahead.
Okay, telnet is used to remotely access devices from different networks.
To access,
SSH.
yes, remote access, remote login. How about FTP?
Transferring that.
Mic check.
Yes, please.
Emails.
FTP.
FTP stands for File Transfer Protocol. It's used to transfer files between different computers on a network.
Very good. Files between
Uses
hosts.
Outlook.
FTP, my friend. Then what will happen when you go to SMTP? Then when you go to
FTP is for transferring files,
Yes.
normal files.
Yes.
Normal files.
Yes.
From one computer to another computer.
Okay. How about
not necessarily the one is going to the web?
Yes. How about DNS?
That is domain name.
Domain name service.
Domain name system, it changes human readable domains into computer like numbers that are understandable by a computer.
Very good. Yeah. It converts our domain name like google.com into an IP address 201.002.156. Guys, if you unmute yourself, please mute yourself after, please. Just be mindful, and you know that I have to mute myself after when I'm done, out of courtesy. All right, so these are some of those things in the application layer, and there are others like the SMTP, like POP3, like IMAP, etc. So they provide network interfaces for applications. Now we have our transport layer, and we say this one establishes end-to-end connections. And we have our TCP and we have our UDP. Now one of these is a secure protocol, and the other one is not a secure protocol. Which one is a secure protocol of these two?
TCP.
Mic check.
You tell me the secure protocol, and you tell me why it's a secure protocol.
The TCP is a secure protocol in that it offers what is called the three-way handshake. And it's comparable, like when you are using a telephone call, when you say hello, the other person responds to say hello in return, can I send you this? And okay, I've received. But the user datagram protocol is not secure because the packets that are sent, they are not reliable. It's comparable to postal services. You post a letter, there is no guarantee that the other person on the other end has received. It's just by chance. Thank you.
All right, thank you. Thank you so much. Very well explained. The TCP protocol, or the transfer control protocol, provides a reliable connection-oriented communication services for applications and applies to applications that require responses. For this guy to send packets, he needs to first establish that the receiver is there. Like our colleague said, hello, are you there? Should I send you this? Then, yes, I'm here. Please send it. I'll be there at 11. Then you go ahead and send. With UDP, it is connectionless protocol, and for it does not guarantee reliable transmission. Whether someone is there or not, you just send the package, like a postal address. Whether they receive or not, you're even not aware until maybe when they tell you sometime that, oh yeah, you sent your package. I received the package. So that is the UDP, all right? The user datagram protocol. All right, so we'll also look at the internet layer, or what we call the network layer in the OSI model. And we have our IP. IP is the internet protocol, and the routing protocol. They usually work together to find an optimal route that can transmit the destination. Because you have sent a packet, but how is the network, or how are the devices going to tell that, okay, this particular packet is going to be sent to so and so, and there are so many routes over the internet, but how is it going to tell that, you know what, when I'm going to this destination, I can either use this route of where you get it there, or I can use, Ginger route, I can use, this route, but the fastest route is this route, so I should take that route to make sure that I deliver this package on time. Okay, and maybe I'm going to make 3 stopovers, or maybe I'm going to get to that destination and then give it to Michelle to also help me transfer, who will give it to Lorraine. Also, Lorraine will help me transfer until when it gets to the receiver. And we also have other protocols like the IMCP, IGMP, ARP, and ARP. Who has heard about the ARP and what does it do?
Mic check.
Go ahead.
So ARP is just mapping of the MAC address and the IP address. Means it just map out. There is a table, and through that table it maps out the MAC address of a computer and the IP address.
All right, thank you. So the ARP helps us to resolve known IP addresses. You know that I am sending this package to 192.168.0.5. But I don't know his MAC address. The MAC address to me is not known. But for any communication to be successful, for any packet to be successful, remember the data link layer, layer 2, we are looking at the MAC address, right? We are looking at the source MAC address, and we are looking at the destination MAC address, but we don't know the MAC address of this machine. So we are going to use this protocol, and we're going to look at it in detail to help us resolve and map the MAC address of this particular IP address to it, so that we have our packet, our quintuple in full. And we're going to be looking at these details later on. So don't worry. So the ARP helps us to do that. And the reverse address resolution protocol, the ARP, basically is also used to resolve IP addresses when a data link layer MAC address is known. So if you know the MAC address, you use the reverse, right? You know the MAC address of the machine, but you don't know the IP address. It will go ahead and it will do the reverse. We also have the internet control message protocol. The most commonly used application in the IMCP are ping, maybe trace route, right? Please mute your microphone. F505. You are breathing quite heavily. Trace route, but basically the IMCP, what it does, it helps us to define the functions of controlling and transferring messages at the network, to check and see the connectivity. Hey, are you there? I'm trying to reach this server google.com. So you say ping google.com, and then it will send the packets and receive response packets and see how long it has taken you the time to leave, and also you will see if maybe, you know, that given server is either reachable or not reachable. Whereas the Internet Group Management Protocol, the ICMP, basically manages multicast group members, and we shall be looking at those details later on. And finally, when we come to the network layer here, we said we are going to look at some of these standards: Ethernet 2.3, PPP, HDLC, and FRS. So the network access layer consists of two sub-layers. We have the logic link layer, the LLC, and also the media access control sub-layer. We shall be looking at those things in detail later on. So encapsulation and decapsulation process. I've already explained this before, that when a sender A is going to send packets to recipient B, sender A here sends a packet, and this packet will be encapsulated. The application layer will get this, data, user data, and it will add on a trailer or like a header of application data, and it's going to encapsulate it and put there the data that is relevant, that is going to be encapsulated. When this data is going to be received here, the transport layer is also going to go ahead and add its trailer of TCP details and the application data, and then it will going to encapsulate that protocol datagram unit, and then it will send the data to the internet layer, which will also go ahead and add its IP details. Is it going to be using IPX or IP? And then the source IP, destination IP, all those things will be included in that packet, and then it will be encapsulated, and the packet will be sent to the network access layer, which will also add the standards. It's going to be using Ethernet 2, and then the IP address here. It will also look at the source MAC address, destination MAC address, and then it will go ahead and encrypt the packet, and then it will send the packet to the recipient. So when it is sent in the bits and streams, ones and zeros, because that's binary, it's the language which these cables and network bit streams are going to understand. And when it is received here, the network layer, this network layer is going to go ahead and de-encapsulate. It's going to de-encapsulate, process, oh, this packet is meant for this destination MAC address of recipient B. Let me go ahead, strip off that, and then it will send the de-encapsulated packet all the way to B. To also go ahead, strip off that, After processing it, process the transport data, process the session data, application data until the recipient receives the packet. So we want to look at one of important concept in this course, the quintuple, because it's going to play a very important part as far as our security is concerned. And this concept, it is a quintuple structure, and we look at these things. We have the source IP address, we have the destination IP address, we have the protocol that will be used, we have the source port and destination port. For any communication for us as security engineers, we're interested in the source, that is 1, in the destination, that is 2, the protocol that will be used, that is 3, the source port, that is 4, and the destination port, that is 5. All right? So those are the things that we will be looking at. Basically, the destination port, generally, it is a well-known application service that have standard ports. Like, let's say if you are sending something through the web, the port will be port 80, isn't it? If you're sending something through the web, HTTP, our port will be port 80, okay? And if you are going to be doing file transfer protocol, depending on the kind of control, you can either use port 20 or port 21, and we shall be able to see the differences. If you're going to remotely access something, it is port 23. And if you're going to be sending emails or configuring your client, usually it is port what? 25. So depending on the domain names system, we can use port 53, and SMP, we can also use port 161. And we have our IP packet, we have TCP, we have UDP. This is for UDP, this is for TCP, and then we have our IP packet. So a quintuple is a concept so that an application server can respond to a service request. It must register the port numbers and a protocol. Either it's going to either use TCP or UDP for the services it hosts. By using the quintuple, the application server can respond to any concurrent service requests while ensuring each link is unique and is unique in the system. Whereas with the source port here, it is generally a common application also. Like, let's say, like HTTP, FTP, and Telnet are assigned to port numbers, but in the range of either 0 to up to 1023. But some operating system may use greater port numbers and their initial ports because source ports are unpredictable and they are seldom involved in the access control lists. Okay, this is what we are calling our quintuple. So let us look at the network layer protocols. The network layer protocols. So we have ARP. We are going to be looking at it in detail. We have SNMP, we have IMCP, we have our routing protocols, OSPF or RIP, and yeah, we have NMS and NetStream, and we shall be looking at some of them in detail. But where ARP, like we talked about it earlier, like our friends told us, when a packet is forwarded to a host or a gateway in the same network segment, the destination address is known and the MAC address corresponding to the destination address is obtained. In the same network segment, the MAC address is used for communications. And IMCP is used to test network connectivity, to check and see, is PC there on the network? Is it up and running? We can use this IMCP, Internet Control Messaging Protocol, to check the connectivity between hosts on the network. And the typical applications for IMCP is usually ping or trace route. So routing protocols like OSPF, Open Short Path Fast, or the RIP protocol, they're used for communications between users in different network segments. Yeah, if you have users in different network segments, they can use those protocols. And the SNMP basically is a protocol, a network device management protocol that is going to help us log into our devices and manage them, right? We'll be using this protocol. And the NetStream here is basically an information sampling protocol, and it's usually associated with other devices such as anti-distributed denial of service attack devices. So let us look at ARP overview. We have already talked
Excuse me,
about,
sir?
yes, please.
Sir, I have a doubt. Sir, suppose PC1 is something sending to PC2 on something like port 80. Suppose there is a scenario that PC1 is sending something to PC2 on port 80. Is it necessary that PC2 will also send to PC1 on that same port?
No.
I have not got your question.
Sir, I'm saying that if one node or means one PC1, sir, in the previous example only, if PC1 is sending something to PC2 on port 80, suppose they are using port 80 HTTP, then if PC2 wanted to send the acknowledgement of that thing to PC1, it will be using port 80 only, or it can use some other ports also.
Depending on what you want to achieve, you can actually configure and you can change those ports, but the default ports, now like for HTTP is port 80. But remember now, they are also source ports attached also. You have a destination port and we have a source port to just make sure that in case there are also other computers connected. All a good example is that you have a web browser here. Let me see if I can open a web browser very fast. You have a web browser here. Just a moment. You have a web browser here, and you have different tabs, right? How is the computer going to know that, you know what, this packet, much as we're using the web, but when I'm sending it back this packet, this YouTube packet or these WhatsApp packets, they should go to WhatsApp, not go to the email, right? So much as we're using port 80, but there are also other source ports that are attached to it, so that when the sender is sending back, he knows exactly which application to send the packets to on your computer. If you're watching YouTube, same time doing your things and doing other things, you use both the source ports and also use the destination ports, and sometimes even the source ports are randomly selected or created by the application you are sending the packets. I don't know if I've answered you because I didn't get your question correctly, but I think it was within that line. So let us look at the overview of ARP. Our colleague said that by using ARP, a network device can establish a mapping between a destination IP address and a MAC address. So after obtaining the destination IP address at the same network layer, then the network device needs to determine whether the MAC address is known. So we know we have our host A here and we have our host C, and we also have this computer here. Let's call it host B, okay? Let's call it host B. And host A here wants to send packets to host B. And for it to be able to send these packets, it needs to be aware of the MAC address of host C, right? These are the two things that are needed. For me to be able to send a packet, I will need a source IP address and a destination IP address, because I need to clearly state in the packet when I'm encapsulating it, I am the one sending it and I'm sending it to that. At the same time, I will need a source MAC address plus a destination MAC address. At this level, let us focus on these things, right? So, but now we know the destination IP address, but we don't know the destination MAC address. What protocol are we going to use? We're going to use the ARP to help us resolve the protocol. So here's the ARP request. I have my host A here, and it has host C here. We don't know the MAC address for host C, and this is host B. What is going to happen? The ARP is going to be in form of a broadcast packet. By broadcast, we have multicast, we have unicast, and we have broadcast. Multicast is to what? Since you have taken long, I'll write it is to many. Multicast is to?
Many.
Okay, then unicast is to?
One.
And broadcast is to?
All of them.
Yes, that's a difference. So here we are going to use, the ARP uses a broadcast packet to send the packet to other computers, because at this particular point, it is not aware of the destination MAC address. This computer knows its source IP address, which is 10.0.0.1/24, and it knows its MAC address, but it wants to establish a communication with host C, but it doesn't know the MAC address of host C. And yet for us to be able to send a packet which will be received, we need to make sure that we know also the destination MAC address. So what is going to happen in our Ethernet frame here, we are going to look at it. We know that we have our destination MAC address, and we see we have put it in broadcast mode. All the numbers are zeros. Yes, as you can see here, this is the packet, and we're going to send an ARP. This is the source MAC address for this machine, and we're going to now put our ARP request. We said, hey, look, I am trying, this is my message. I am trying to reach hosts, which is on this IP address of 10.0.0.3, which is this guy, /24. And this is my source IP address. I'm at this address, this avenue. Please find me at 10.0.0.1. And this is the destination MAC address. I don't know. That's why I am blank, 00, broadcast, okay? I am blank. So kindly just help me reach out. Just send to all the neighbors so that—
Mr. Ssendi.
Yes, please.
Sorry for disturbing you, sir. You know, we're trying to follow, and the charts that are popping, some of them are not helpful. Like people are complaining to say I have network issues, and when it pops, it covers some content that we want to focus attention on.
It's destructive on our side. Distracting a lot.
Thank you.
Okay, at this point, I've disabled the chats.
Yes, please, thank you.
Thank you.
All right. You can, okay, so I'm trying to say that I don't know the destination address. So just send to all the neighbors in my network or in my neighborhood. And then for me, I can be found on this address. I live here. This is my address. This is my physical address, right? So this is 0.1.00.3.AA. So you can find me there. And the operation type is a request. So this guy is going to go ahead and it's going to send the ARP request. All right. So this message is going to go, and it's going to go in a broadcast mode to all the machines on the network. Okay. It's what we are calling the ARP request. But the thing is, remember, before we get there, we have two things. We have an IP address. I've been talking about an IP address. And an IP address, and we have the MAC address. Who can tell us the difference between IP address and MAC address? Because these two, we need them when we want to communicate or send packets. So what's the difference between an IP address and what is the difference between a MAC address?
Mic check.
Yes,
Mic check.
go ahead.
Yeah.
IP address. Mic check.
Go ahead.
Mic check.
So mic check, the first one you speak.
An IP address, it is not fixed as compared to a MAC address, which is fixed when transferring addresses.
Okay.
Mic check. An IP address is an address.
MAC address is the physical address of a gadget, a networking gadget. For example,
Mic check.
Someone
mic check.
Yes.
A MAC address. A MAC address is an address which is given to the computer by the
Someone has a key. Please.
Okay. For me, I think MAC uses physical addressing and IP logical addressing.
MAC addresses are layer 2.
MAC address is an address which is given to a computer by its manufacturer.
Okay. All right. Thank you all. So here, a MAC address, it is burnt. It comes together.
For me, I think MAC uses physical addressing and IP.
Okay. Uses logical addressing. So the MAC address comes burnt here on on our network interface card, and it doesn't change. It is physical. Every device that connects to the network, your phones, your routers, your PCs, everything that connects and has a network interface card comes embedded. Please, Nathan Chulu, I'm going to remove you from the call. You have a kid and you keep unmuting yourself. Please, do not get to my nerves. I have muted you like 10 times and it's becoming irritating. Okay, so, and then the IP address is a unique identifier for every machine on the network, and it is a logical address. It's not physical like the MAC address. This one is physical. It is burnt on your physical network interface card, right? And the IP address, it is a logical IP address. It can be dynamic. You can configure it to be static, but it can change depending on the network you have connected to. And you need both these two to be able to establish a successful communication. I hope now for the people who have never done some networking, you'll get the point why we're now focusing on making sure we resolve both the IP address and the MAC address. Now here we are saying, we don't know, we know the IP address.
Mic check.
Yes, Makona.
Excuse me, sir. What is the meaning of FCS?
It's a frame checksum. That is just checking to see if the frame has not been tampered with or it is complete. It's just checking to see whether the frame is complete, or if it's not, then it will discard the frame. But since we are not doing a networking course, we don't focus so much on the things I've not paid attention to. But thank you for asking.
Mic check.
Yes, please.
From what you have said, does it mean the IP address will change according to the net, depending on the network, but the MAC address is the same throughout?
Yes, please. It doesn't change. It is a chain. Even your devices, your mobile devices, any device that connects to the network has a physical MAC address, and it doesn't change. But for those who are interested in delving into more, you can do a networking course like Datacom, where you actually dive into MAC addresses, how they are, who makes them, how they come up with them, the bits for MAC addresses, etc, etc. So now let us focus, please, on the ARP request. And we are saying we want to establish a connection and send our packets. We have a package for C, but we don't know his physical address, right? Because we say the IP is the logical and this is the physical. We know the logical, he's within the neighborhood, within our segment, network segment, but we don't know his physical, where he stays. So we are going to use the ARP protocol to help us resolve this person's name, the IP address, to his physical address. So we're going to send the request and it's going to go in broadcast mode. So what is going to happen when the packet comes here and it's going to reach host B? Host B is going to receive it because it's in broadcast mode. Even if there was another computer here, host D, it will also receive it. Even host E will also go ahead and receive it. But what will happen? Host B will look at this information here provided to him. He will look at it and say, okay, the destination IP address is 10.0. No, that is not my name. This email, this package, this request is made for someone else. So it will go ahead and discard. My address is 192.168.1.2. So I am not supposed to receive this, so it will just discard and it will not do anything. It will send to neighbor E. Someone will knock on neighbor E. Hey neighbor E, are you so and so? Are you 10.0.0.3? A neighbor E, no, I'm not the one. He will shut the door and discard the packet and you do nothing. So when the packet comes here to host C and asks, hey, are you 10.3.3? Are you 10.0.0.3? This guy will look and be like, yes, did you have anything for me? Yes, I actually have a package for you. What is your physical address? No, I live at this address of 00010203.cc. Oh yeah, I'm the one. Okay, then this guy will take note and will be like, oh, I have a package from you coming from this address. This guy here called 10.0.0.1, and he lives at this address. So please take note. This guy, since because he wants to learn, even the switches or even him, he'll go ahead and update his MAC table his ARP table, and then he will say, okay, so whenever I need to communicate back to this guy, he lives at this. So let me address him, and this is his IP address. Okay. So what will happen? He will go ahead and he will send the ARP request. Remember, all these other guys who are not the intended recipients will discard the packet, will just drop it. They have nothing to do with it. The communication is not meant for them. So they'll just drop the packet. And when it reaches host C, now he'll reply back and say, yes, I am actually that guy. So he will send a ARP reply packet, and it will go. And after him doing that, before actually he does that, he will also go ahead and update his ARP table, and he will say, okay, I have discovered my neighbor of 10.0.0.1. He lives at this address, or this MAC address, and he lives there. And his type, he was assigned this IP dynamically or statically. So please store his records. Whenever you need to communicate to him, these are going to be his address. Store them and keep them safe. So this guy will go ahead and send the reply. And this guy will also learn about this guy's MAC address, and he will also go ahead on host A and update his address, and he will put there the address of that guy and also the physical address of that guy and also the type. And then he can now successfully be in position to send the ARP, to send the other packets and establish the connection. So when this guy is sending back the packet, he sends it back. He's like replying, you know what? I am sending, this packet is supposed to go to 10.0.0.1, and this is my IP address, the one he tried to reach out to me. This is my MAC address, and the source MAC address, because I know it's this guy who, this is his IP address, and the source MAC address, I know it is mine, it is here. So kindly go ahead and reply back to that guy. If you notice, this frame is in unicast mode, right? The reply form is in unicast mode. Why? Because it already knows the destination MAC address. The destination MAC address, it's only replying back to this guy, and it's only this guy which will receive the packet. And then the source MAC address, it is his MAC address here, and it's a guy who is sending the packet. Okay, so moving, we have Gratuitous ARP, and this Gratuitous ARP can be used to detect whether there's an IP address conflict. Remember, one IP address uniquely identifies a host on the network, and only one host can have one IP address, which is the same on the same network segment. So meaning, for them to make sure that they don't have the same names or same IP addresses, we have a protocol called Gratuitous ARP. It is used to detect ARP conflicts. What happens here on host A, after maybe let's say the dynamic, the DHCP, after the DHCP server assigns an IP address dynamically to this guy will now be like, oh, I've received this IP address of 10.0.0.1, but now I need to confirm if I'm the only person with this IP address. So he will go ahead and send an ARP, and send a Gratuitous ARP to the network. And you can see here the destination MAC address is in broadcast. Why? Because it wants to send the packet to all hosts on that very same network segment. And then the source IP address, the source MAC address will be his MAC address. So the ARP, Gratuitous ARP, will go with a destination IP address. And as you can see, the destination MAC address, such this guy is the one who is sending the packet, but the destination MAC address, it is his MAC address, right? And as you can see, the source MAC address is still his address. The destination MAC address is a broadcast MAC address. And then the source MAC address, it is his MAC address. So he will go ahead and will send the packet to everything. So what happens if there is another host in the network here, host C or host B, and he's having the same IP address? Remember, since he's an ARP, he will have to reply. But now if he replies, then this guy will know, oh, actually there's someone else with that IP address, so it will reject the IP address, or it will notify you that there's an IP address conflict on the network. All right. But then after him is the only one who is supposed to receive the packet because he has sent it to his IP address. And if there's no reply, then it means that this guy or there's no conflict within that network segment. Let us look at the IMC, and we are saying that ICMP is used to transmit error, control messages, and query messages. So IMCP is one of the core protocols in TCP IP protocol stack, and it is used to control packets between IP networks to transmit error, control, and query messages, right? So if you wanted to communicate and establish and see if this guy can reach this other, you can use the IMCP. What time is it? You can use the IMCP protocol to be in position to communicate with the network. So you can use either the ping command or the trace route command, basically to determine and see what route is going to be taken from one host to reach the other host. So one of the most common application, IMCP ping application, IMCP application is a ping. Ping, you just say ping, and then you state the address of the server or the host you are trying to reach. So here, a typical application is the ping command. And the ping is a common tool for checking network connectivity and for collecting related information. Let me say I have my, just a moment. I want to make this bigger. Okay, let me say I have my computer here and I have my other computer here, and they are connecting in between here. We have our switch. We have our switch here, and let me connect them using a copper cable and connect them. Go ahead, come here to PC1, go into its configuration command and give it a static IP address. Let me give it 192.168.0, the 0 network, then give it an IP address of, let's say, 7, right? And then come here. Okay, to make it easy, let me just give it 1 so that we can easily remember. Then the subnet mask is in class C 255.255.255.0, and then the default gateway, I'll leave it blank, and then I go ahead and apply. I come here, this PC, and also give it configurations and give it an IP address of 192.168.0, and then give it .2, and then go ahead and give it a subnet mask of 255.255.255.0, and then go ahead and apply. I will not give it a name, and then go ahead and apply. Okay, and then come and get another PC, and I'm going to put it on the same, a different network segment, and put it here, and then go ahead and connect it on my switch, and then go into its configurations and give it a network IP address of 192.168, and then give it a segment of .10, and then .10, and then give it .1. And then come here and give it a subnet mask of 255.255.255.0, and then go ahead and apply. And then after, I go ahead and select all my devices and then power them on and wait for them. I'll just open my switch console here to see and wait until when it has been powered on. Okay, it will hash, and then boom, it has powered up. And we can go ahead, status is up, and wait. Okay, just a moment. Status is up, status is up. Okay, okay. And then display interface brief. I'll see that I've connected my on Ethernet 1, I've connected the computer, it's up and running, and Ethernet computer, I've also connected the computer and it's up and running. So I know this IP address here, and I am going to open this computer. Remember, just to give it a label, this one was at 192.168. Oh, wait. 192.168.10.1, isn't it? And I remember this one, I had given it an IP of 192.168.0.1. And this one, I had given it an IP, please mute your microphone, an IP address of 192.168.0.2. So if I wanted to check, I would use the ping command to try and check connectivity and see if I can reach PC here of this address. So I can open the command prompt on this machine, and I say I want to see if I can access, if PC2 is up and running, right? So I'll say ping 192.168.0.2, and then hit enter, and then you can see it has sent packets, and it is also getting reply from this machine. It has successfully sent packets, and I've received back the packets. If this machine was powered off and I have stopped it now, right? And I came back to this PC and I'm trying to see if I can reach it, and I press ping. Are you seeing what is happening on my screen now? So if I was a network engineer and I was in my server room and people are telling me they can't access the file server, one of the first things I can do is first to check its connectivity. I would just run a ping command to that file server to just make sure if I can access it. As you can see, I've sent a ping command here and I'm not getting any request because my PC is off. If I powered it back on, I go and check, oh, actually, the switch had accidentally switched, powered it off. I go ahead and power it on. When I ping it again, you will see, because it's just starting, let me just wait to see if it has successfully started. I think it has successfully started. So when I come back and ping it again, okay, it has not yet started. I've just started it. Let us just wait a bit. In the meantime, let me also try and ping this PC, which is on this network, right? I go ahead and ping 192, ping 192.168.10.1 to see if I can be able to reach it. Are you seeing what it is telling me? Boom, host unreachable, but it is powered on and it is running. But because we are using a layer, we are using a switch which does not have routing capabilities, and remember it sends out packets within the same network segment. Okay, and this guy is within a different network segment. If I came here and added another PC and connected his PC using my copper cable and connected this PC to my switch and went ahead and powered it on, went ahead into its configuration, gave it an IP address of 192.168, gave it the same network segment as the other one, and gave it .2, and then go ahead and apply, and then rename it and say this one is on the network segment of 192.168.10.2. So
excuse me, sir.
And go ahead and power it on. Yes, please.
You didn't give the second computer on this network a subnet mask. Does it matter?
Oh, this one?
Yes.
Okay, let me give it 255. Thank you, 255.255.0, and then go ahead and apply. All right, so if I went into this PC now, right, which is in the same network segment with this guy, and I went into its command and I say ping 192.168.10.1, this machine here, and then hit enter, then you can see that I can receive a reply packets from that machine, meaning that that machine is powered up and it's on and running. So here, basically, the most common application is the ping command, and basically, when you run it, you can have different parameters, like the parameter A. Basically, you specify it when you want to select the source IP address. The default IP address of the source interface is usually that address. Parameter C is specify the number of echo requests to be sent out. The default is 5. And parameter D is specify the source debug option of the socket being used. And parameter F is to set do not fragment flag in packets IPv4 only. It works on IPv4. Parameter H specifies the time to leave value for echo requests to be sent. The default is 255. And parameter I select the interface sending the packets. So this is basically an example. You say ping and then specify the IP address, and then it will send the request and then bring them back. This is just what you have just seen on ENSP. It's just an example. So the IMCP.
Check.
Yes, please.
Excuse me. You said that it's not possible for a computer to access the other computer if they are not on the same network segment. Then how is it possible to connect to a computer, another computer that's not on the same network segment?
That's why layer 3 comes in for routing. And then that's why you have a default gateway, right? We shall get there, don't worry.
Okay, thank you.
Okay, just like you are in a fence at your home in lockdown, right? You can access all the premises in your compound, right? But for you to be able to get access to your neighborhood, you need to have a gate where you can pass, and also maybe a car that will drive you and also get access to a gate of your neighborhood so that you can be able to access to everything inside their connection, isn't it?
Yeah.
But we shall get there, don't worry.
Okay.
So another application is basically the trace route application, and its application is it traces the forwarding path now of packets hop by hop based on the time to leave value packet. In the header to trace the path of specific destination, the source end first, and then sets the time to leave value of the packet to 1, sorry. So after the packet reaches the first node, the time to leave, then times out. And then therefore this node sends a time to leave out message carrying the timestamp to the source end. Then the source end sets the time to leave value of the packet to 2. And then after the packet reaches the second node, then the time to leave value reaches out. I'm going to explain that in a few. So what happens here when you want to determine, right? Like you have just said, we have one network segment. Now, what happens if you have, different network segments, or maybe you have even so many devices on the network, or even different routes? How do we determine which route to take, and how are we going to determine how we are going to be able to reach host B? Like you can see, we have this route that goes through this, and we also have this route that goes through there, right? Just like when you're going to a place, you can have different routes, isn't it? You can board a bus that is going to make 5 or 4 stops, or you can make a bus that is going to make 3 stops. So what happens, there's an application protocol called the trace route protocol, and it can be used to help you trace the number of hops in the system, or also the route. So what happens when you send a packet here, it's going to set the time to leave value equals to 1. So it will set it here, and it will come to this interface when it is equal to 1, and then it will be 1 here. But when it is leaving the interface, it is timed out, it is reduced by 1, and then it will be 0. So when it is reduced to 0 and it reaches the next device, then this device will go ahead and discard the packet if the time to leave is equal to 0. It will discard the packet and it will send back a reply with a timeout saying, you know what, the time to leave has expired. Please act accordingly. So when this guy receives that packet, it will go ahead and increment the time to leave +1. So when it comes, the packet time to leave packet now will be 2, isn't it? Will now be 2 because it has incremented it +1, which is equal to 2. So it will come when it is 2 here. When it is leaving out on this interface, it will be reduced by 1. So it will reach the interface when it is 1, isn't it? So this guy will receive the packet because the time to leave is not equal to 0. It will receive the packet, and after receiving the packet, but when it is also sending it out here, it is going to subtract by 1, meaning the time to leave will be equal to 0, and then the packet will go. When it reaches this interface, this guy is going to discard because the time to leave is equal to what? To 0. And it will send a reply that, you know what, the time to leave is equal to 0. There could be other hopes. Please act accordingly. Please mute your microphone. You have noise in the background. Joseph Kaboto. Okay, so where was I? Okay, so this guy is going to go ahead and send back the packet, and then this guy is going to increment by 1, right? It's going to go ahead and increment by 1. So it's going to be equals to 3. They will receive the time to leave packet when it's equal to 3. And then when it is sending out from this packet, the time to leave will be equal to what?
Mic check.
2, yes.
It will be equal to 2.
Yes, it will be received here when it is equal to 2. When it is sending it out from here, it will be equal to what?
1.
1. This guy will receive it when it is equal to 1. And when it's sent out here, it will be equal to what?
0.
Equal to 0. And this guy will he receive the packet?
Discard it.
No, to be
Discarded.
Discard the packet and send back a reply message that, you know what, the time to leave, there could be other hopes in the network. Please kindly increase. This guy will go ahead and add a +1. Now it is equal to 4. And it will, when it comes here, it will be 4. And after, when it is leaving this interface, it will be equal to what?
3.
3. You receive it when it is 3. When it is leaving the interface, it will be equal to what?
2.
2.
It will be equal to 2. This guy will receive it when it's 2.
1.
When sending it out, it will be 1.
1.
This guy will be equal to 1. When he's sending it out, it will be 0.
0.
He will now receive the packet. But now, this guy will be able to know, oh, so if I'm using this route, I have gone through 4 hops, right? So there are 4 routing devices that I must go through, or devices that I must go through for me to be able to reach host B if I'm using this route, isn't it? Now it's going to do the same to check and see how many hops are on route B. So let us do the same for route B. We say that default time to leave in trace route is going to be equals to
1.
To 1. So it's going to send it 1. It's going to receive it. When it's sending it out, it's going to be 0. This guy will not receive it. Discard. This guy will go and add 1. It's going to be equals to 2. Going to send it when it's equal to 1. This guy will receive it when it's equal to 1. Send it out when it's equal to 0. This guy is going to discard. He will go ahead and increase +1. This guy is going to receive it when it's equal to what?
3.
When it's equal to 3. Send it out. Here it's 2. Send it out here when it is what? 1. This guy will receive it when it's 1.
0.
1. So this guy will note that there are 3 hops on route B, isn't it? So it will use that analogy to determine and say, you know, whenever I want to reach host B, I think that optimal route for me to get to host B will be this route. Why? Because I'm only going to go through only 3 devices. And if I use the upper route, I need to go through 4 hops. Is that okay? So trace route, like I said, it is used to trace the different routes and also to determine how many number of hops a packet must hop and hop from here to there until when it reaches the final destination. So it also has different parameters. When you get time, you can go ahead and look through them. So the traceroute command displays each hop that the packet trace passes through during the network transmission, just like I have established. So we also have the routing protocol overview. Routes are classified into types like either network segment routes, host routes, direct routes, indirect routes, unicast routes, multicast routes, dynamic routes, static routes, basically depending on the nature of routing. And routing is one of the most basic element in data communication network, because now we are looking at the same network segment. But what happens if I need to go out of that compound and also go to another network segment? Then routing plays a very critical role as far as that is concerned. So it is a process of selecting paths on a network through which packets are sent from one source to the destination. And let us look at one of the protocol, the open short path fast. It has these benefits, no loops, fast convergency, scalable, and also supports authentication. So OSPF is a routing protocol and based on link status, and it ensures that the network topology is loop free. There's no loops in our network topology. It also supports division. You can divide your topology into different divisions, and routers in an area, you divide them into different areas. Use the shortest path fast algorithm to ensure that first there's no loop in that area, and also to ensure that interconnection rules to ensure that no routing loops exist between the areas. OSPF can also trigger rapid, detect and advertise topology changes in an area. So if the router, the master goes off, the OSPF can be able to, automatically vote for the backup master, and then boom, your network topology is up and running, and the open short path fast is at play. This is not a networking course. We shall just mention some of those things and move forward. And then we want to introduce ourselves to SNMP. SNMP is used to transmit management information between network management systems and managed devices. If you want to control this switch, you're going to use this protocol to be able to access it and then change configurations, make backups, restart it, and do all sorts of other things that you need to do. All right. SNMP structure, this is the structure of NSMP. It introduces the NMS agent and MIB, and the agent is a process performed on managed device, whereas the MIB is a database that contains variables maintained by managed devices. Then we have enterprise. Yes, please.
This is Ssendi. Just to benefit from most of these acronyms, would you mind mentioning them in full, so that we are aware of what it means, the abbreviation?
Some of them I had already mentioned them in full, like NSMP, like the NMS, network management system, like the simple network management protocol. Remember the first slide, I mentioned them, but worry not, you're going to get these slides. You're going to get these slides, and also I would strongly advise, if you meet some of these terms and they don't make sense to you, you can just go ahead and Google, but I'll try my level best to make sure that I basically give out the acronyms in full. But in networking, most of the times we just say out the acronyms. But for your own benefit, I will try my level best to do that. All right, so here, just basically an example. You need to, yes, please.
Hello?
Yes, Tembo.
Yes, Mr. Samuel. Just a concern, what's the best way of asking questions? Are we supposed to be raising hands through the reactor, or we are just supposed to come in? Because I've been initially raising my hand. It appears you are not recognizing my hand, and people are just asking questions, interrupting the session. So I need to understand, should we just be coming in while you are lecturing?
I think for the best experience and for the best experience of the recording, it's advisable we ask questions at the end. We ask questions at the end, and it's important that you raise the hand, just like you have done. I had seen it, only that I wanted to come at the end so that we don't, interrupt the network, unless when something is really, really burning and it's affecting your ability to continue in the class. But should you want to ask something, you can just note it down. If it can wait, then usually it would be advisable. Imagine if you're watching the recording and you're going through these sessions and drills and this kind of conversation. Would it be interesting to you to watch? I hope you're getting my entire idea.
Yes. No, that's fine. That's fine.
All right. So enterprise network operation and maintenance. Basically here, you just need to understand the traffic trends of all the branches and identify the devices that the branches need expansions. You as a network engineer, and also need to analyze the distribution of branch traffic and identify the value points for capacity expansion, rank the changes in branch traffic, and also allocate existing network resources accordingly. Here as an IT engineer, maybe you have exhausted, you go to your manager or supervisor and tell them, you know what, I've exhausted all the bandwidth on this port and we need to purchase new devices to expand the network capacity. Supervisors, them being supervisors, they'll ask you, are you sure you need to expand the capacity? Is the network fully optimized, or is the service application developing rapidly? So if you do your job well, you should be able to know that, you know what, I have done a detailed network application development reports for each branch, blah, blah, blah. And if you can look at it, this justifies my reason why we need such devices and why we need to expand the network. So the NTA concept, it is basically the network traffic analyzer. It is one of the most commonly used is the eSite. It provides users with reliable and convenient traffic analysis solutions. It also helps to monitor network-wide traffic, and most importantly, in real time, and also provides multi-dimensional traffic analysis and reports. Okay, so this solution helps users not only to detect abnormal traffic in a timely manner, but also to learn about network bandwidth usage and also traffic distribution. It also, in addition, helps enterprises implement traffic visualization, fault, query, and also planning. Okay, so it is a software-only solution. No hardware is required for you to implement it, and no additional investment is needed. The NetFlow, StreamFlow, and SFlow protocols are used to collect and analyze common IP packets, provide a customer analysis report, and monitor network-wide traffic in real time. This is a powerful tool for enterprise operations and management. Functions, the eSite network traffic analyzer provides a convenient way to monitor and analyze networks by using IP network traffic, and also by using IP network traffic and information provided by network devices that support NetFlow, NetStream, and SFlow. The eSite network analyzer analyzes network-wide traffic, provides traffic analysis reports, display traffic analysis results in various charts, and this helps us as users of those devices to learn about network traffic-wide traffic, and also including the traffic distribution, and also detect abnormal network traffic. This is the NetStream overview. And we are saying that NetStream is a Huawei patented technology used to collect and distribute statistics about network traffic. And it uses the network device that sends and obtains statistics to the network console center and for further processing, and sends the statistics of the NDA for analysis. The results of the analysis provide a basic or the basis for network accounting and planning. So the data analyzer, the NDA, usually is used to analyze and process the statistics and also generate the reports, and also provides a foundation for various services such as traffic, changing, network planning, and monitoring. Whereas the network connector, collector, the NC, the NSC, basically its job is to make sure that packets from, the data exporter are sent to the database to be processed. The network exporter, the NDE, it is samples the traffic and exports the traffic statistics, and it is sent out for analysis. So we want to look at transport layer protocols, establishing TCP connections. Our friend already talked about the handshakes, and we said that TCP is a secure protocol because it's connection oriented. For you to establish a connection, you must go through the hello, are you there? Yes, I'm there. Okay, now we can start communicating. So you have a client here, you have a server, and you want to establish a connection. You have to first send the SYN packet, which will be received after the SYN packet will be sent back. It is SYN plus acknowledgement. SYN plus ARC is the second packet. It is usually sent back with an acknowledgement number plus number 1 of synchronization A. And then after the client receives the SYN plus acknowledgement, it will send the acknowledgement packet to the server and telling it, okay, thank you for responding. I have now established, we can now establish a good relationship. So please let us start communicating. And then the server will, the connection will be established, and then the client can either receive a packet or send a packet from the server. So it is a three-way handshake. Things to note: first packet, SYN pack. After a SYN is sent, the server responds with a SYN plus acknowledgement. That is a second packet. After the SYN plus acknowledgement has been sent to the client will send the server the acknowledgement packet. Now, you know what? Thank you for establishing. Let us now start communicating. So disconnecting has four-way handshake. When you are done communicating and you want to rest, so the client A here will send the fin or the finish packet, and it will send it there. You know what? I am done. I am done accessing whatever I had to access. So please, I want to terminate the connection. This guy, after terminating the connection, will go ahead and send back an acknowledgement packet. After receiving this fin packet, it will send back the acknowledgement packet. Same time, it will also send back the fin plus acknowledgement packet. That makes it the third packet. And then after, the user will now be like, okay, I acknowledge that we can now end our mutual connection, and then the disconnection is complete. Let us look at some of the application layer. We have looked at some of these, and I'll not still spend a lot of time on them, but we have looked at the FTP server. The FTP protocol, we said, it refers to the file transfer protocol, which is used to upload and download files. When you're uploading files from my site or from any site that you will be accessing, remember you're using what we are calling the FTP, right? One or another. And then we have the web server, which is basically going to be using HTTP or HTTPS, depending on the socket layer. And then we also have our DNS server, and we said what DNS is, that it refers to the domain name resolution protocol, which is used to resolve the domain names to IP addresses. We also have the mail servers, and they have different protocols such as POP3, such as IMAP, such as SMTP, etc. So let us look at how the domain, the DNS works. So you've been wondering, now I have google.com, how, I've typed it in the browser and I've sent. Because initially, let me just open my CMD here to see some of the servers for Google. Let me say, under normal circumstances, if I wanted to access Google, I would have to cram this IP address. Are you all seeing it? 216.213.58.223.78. That is one of the IP addresses that I can use to reach Google. Of course, Google has quite a number of them. That is one I could use to reach out to Google. So imagine if whenever you wanted to access google.com, you had to come into your browser and type in and type in, let me put this here so that I can see it, and type in 216.5.223.78. Imagine, and you have to cram those numbers, right? And then it will take you to google.com. Imagine if you had to go to LMS, if you had to go to sendis.com, sorry, ping sendis.com, and you had to cram this IP address, right? And then you, whenever you have to visit it, you go, and also you have to cram it and remember it. So you come to your browser and you say ping. So you don't say ping, you say, okay, I want to go to Sendis. You go to your books, it is 50.87.123.37, right? .37. Okay, if I access it, it will take me to IT. Sendis, I've not put the port number, but it will take me to that site which has the website for sendis.com. Imagine if I had to, whenever I had to do all those things, I had to go through all that labor of remembering, of having to remember all the IP addresses of all the sites. How many sites do you visit in that day? I can imagine there are quite a number of them. It would be a bit unfair for you to remember those IP addresses. That's why we are saying we need the domain name server to help us translate. For us, we don't have to remember. Now, if I wanted to access Huawei.com, how does it work? The domain name resolution is performed by a dedicated domain name system, which is called the DNS, and it involves the following types. We have what we are calling a root server, we have a top domain name server, we have a recursive server, and the cache server. And we're going to be looking at those things and get to know what those things are. But basically, the domain or the top domain, the root server is primarily, let us first look at the root server before we get to other things. We are saying that the root server is primarily used to manage the main directory of the internet, right? It is used to manage the main directory of the internet. The internet, everything you're accessing on the internet, we are using the root server. And you may be asking now, where is that server? Because for you, you thought that files are up there somewhere, somehow. My dear friends, there's a server somewhere, a physical computer somewhere where all those files, the files we are accessing, all the name domains and everything is actually being stored. So the number of root servers are limited, and we only have, to date, we have only 13 root servers and we have 13 root server addresses in the entire world. And among those 13, we have, I think, 10 in the USA, 10 are in the USA, and the other 3 are in UK, and then Japan and Sweden, okay? Japan and then Sweden, the other 3 servers, the root servers. So although the network has no boundaries, but still servers have national boundaries, and all root servers are managed by the Internet Domain Name and Allocation ICANN, all right? And Allocation Number Agency. It's what they call ICANN. It manages all IP addresses, and it is authorized by the government or the US government. We also have a top level domain we have looked at the root server. Now we also have the top level domain, and with the top level domain, it's a server used to store top level domain names, okay? Top level domain names are domain names like .com, right? Like .uk, like .co, .ke, .ug, I don't know what you use in Zambia, but I'll just say .za. I think that is South Africa. I don't know. I don't know. Z what? ZM.
ZM.
Yes. .zm. So these are top level domains, okay? And they are stored at the top level domain server. We also have what we are calling a recursive server. And with a recursive server here, we are basically looking at an authoritative server. It stores definition domain name records, yeah? The resolution relationship between a domain name and an IP. They are stored in a recursive server. So after there's been a resolution, the resolution will be stored in the recursive server. We're going to see how it works by giving an example. So it will be stored there. Imagine if every time a user had to access and the process had to be, you have to go through that route, and then from the route you go through that, then it will really have a lot of traffic and resources that are being consumed. So that's why we have a domain recursive server. But also better yet, we also have what we are calling a cache server to help improve on the processes. And the cache server is basically equivalent to a proxy of authoritative server, the recursive server, like a proxy. What it does, it helps to catch, please, Denver Parachi, mute your microphone. It helps to catch that the domain names that have been resolved, so that whenever user accesses that website the second time, it doesn't have to go through the entire process. It will just be able to send back the details. That's what we are calling the cache server. So it works in this following way, right? There is a one Patrick who wants to access Huawei.com to access, to register for my class. But for the very first time, we don't know the IP address of Huawei.com, but we know its domain name. It is www.huawei.com. So Patrick goes into his web browser and he types www.huawei.com. And then he will send a request. You know what? I want to send a request. I want to access Huawei.com because I need a class I want to register to. The request is first sent to the cache server to see if there's been anyone who has ever visited that site and the details are cached. And if no one has ever visited that time for the very first time, the cache server will be like, hey, okay, I don't know about this. I now need to ask my speedias, my experts, to see if actually there's any IP address that is attached to Huawei.com. So the cache server will go ahead and will forward the packet of Huawei.com, that request, to the root server. It will send it to the root server to tell it, root server, what is the IP address for this Huawei.com? Someone wants it and I don't know it, but please, you're the master, kindly help me access it. Then the root server will cross check and will be like, okay, the IP address of .com domain name server is this, right? Because now this guy is the one who has all the IP addresses that are taking us to the top level domain. So it knows the top level domain server where they are. So it will tell the cache server, if you're looking for .com, it's on this IP address. If it was .zambia, if kindly check on maybe y.y.y, that's where you get all the domain names there. So it will be like, since it's .com, please check on ipx.x.x.x. You'll find the details you want from there. This guy will be like, okay, cool, thank you. Let me engage ipx.x.x. So he will send also the request. Hey, they have told me you're the custodian of the top level domains of .com. What is the corresponding IP of Huawei.com? I want to access the files from there. This guy will be like, oh, you're looking for the IP address of Huawei.com. Now their server or the authoritative server where their files are stored, kindly go to y.y.y. You will get all the details you want. So like, okay, cool, let me check the authoritative server. The cache server will now go to IP address corresponding to Huawei.com and ask it, please help me with this IP address. Do not forward me anywhere. They told me you're the authoritative server and you're in custody of those domain names. The recursive server will be like, oh, you're looking for Huawei.com. It's actually z.z.z.z. You can reach their servers using that IP address. This guy will be like, oh, cool, thank you so much. I have now understood. But before it even sends it back, it will also go and update its cache and says whenever another user comes or whenever this same guy comes back here and they want to access Huawei.com, the domain for Huawei.com is this. So I have to make sure I remember it and I store it. So it will go ahead and update its cache details and store it. So it will respond back to this guy and tell the guy that, you know what, the IP address for Huawei.com, I've finally figured it out. I am such a genius. It is z.z.z. So kindly go ahead and blow yourself away. This guy will be so happy, fast access. And now when he comes back the second time, or even another, another African comes back to access the site, this guy will not bother. He says, I would like to visit Huawei.com. This guy says, haha, Huawei.com, I remember it. It is in my cache. Its IP address, it is z.z.z, thus improving on the performance. And then how FTP works, if you want to send a file, receive a file over the network, FTP, like we said, it's a file transfer protocol. It provides an effective way to upload and also download files. Most of you send yourselves files on WhatsApp, images, and you download and even are unaware of the protocols you're using. Yes. So if you want to upload and send files between a server and a client, we use this protocol to transmit the data. FTP establishes a control connection and a data connection between the server and the client, right? So whenever you're uploading or downloading one or another, you have used some kind of FTP. So a user comes here at the user interface, click on the icon for attachment, go ahead to upload the files. So what happens? It's going to process the control, and then it's going to establish a control connection. It's also going to establish a data connection and the data transmission that will be taking place. So the process control works together with the data transmission process to access a file system and also to make sure the file system is sent back to the end user. So FTP is used to transfer files, and we already said that two TCP connections are used. The first is a control connection between the FTP client and the server, and you need to enable port 21 if you're going to use the control connection, and wait for the client to send a connection request. So the FTP client enables a random port number and sends a connection request to the FTP server, and the connection is used to transfer control commands between the server and the client. This is the control connection, and we're using port 21. Now, when it comes to the data connection, which is the second connection between the FTP server and the client server, the FTP client, the server uses a TCP port 20, and here it is coming from the server. It uses TCP port 20 to establish a data connection with the client, and generally the server actively establishes or interrupts data connections. Okay. All right. So that is how FTP works. So FTP mode 1, we have two of them. We have active and we have passive mode. In active mode, which is used by default, usually by default we use active mode, the client sets up the control connection and the server sets up the data connection. In passive mode, at the same time, the client sets up both. That's a difference. In passive, client sets up both. In active, the client sets up the control connection and the server sets up the data connection. But users can switch between the modes throughout the commands. So FTP connection setup is in active mode. You can see here, the client here will set up the control connection to the server, and the server respond. And whereas when you say data connection, it is only established by the server to the client. That's why it is, and remember that data connection, we said this is on port 20, whereas the control connection to send the control commands, it's on port 21. FTP connection setup in passive mode, we said both of the connections are set, the control connections are set, established by the client, and also the data connection is established by the client. That is in passive mode. We looked at HTTP, HTTPS, basic concepts of the web application. we have already seen these things and we have talked about them. And we said a web is built on a client server architecture and relies on the essential technologies using HTML, the URL, the resource unique allocator, and also the protocol that is going to help us to transfer those hypertexts. All right, so these are some of the things we have already talked about them already, and they're not making news to us, so I'll just leave it. But like I said, HTTP is a stateless protocol that uses a request response method for communication. If you say, hi, are you there? This guy will say, hey, what can I do for you? And then I need to access this file on this browser. And they say, do you have the key? Are you permitted to access it? Yes, my key is actually here. And then you'll go ahead and give them permission to access the file. HTTP has two types of packets, the request packet and the response packet. The request packet is sent from the client to the server. The response packet is sent from the server to the client. SMTP, POP3, IMAP, these ones are protocols for sending emails. I know most of you have gone through them, even when you're setting up Gmail on your phone or mail client on your iPhones, you somehow interface or play with such protocols. So how mail is sent and received, SMTP defines how PCs send mail to SMTP server and how mail is transferred between SMTP servers. The post office protocol, which is POP3, an internet mail access protocol, specify how CPs manage and download the mail on the mail server through the client, whereas the SMTP and POP3 are deployed on the mail server by administrator, and the mail client software such as Outlook or Gmail client or any other application is installed on the user PC. This is just an example to see you how a mail is sent and received. Now we come to this quiz and I will ask you a question. Which of the following is not the TCP/IP model? Which of the following is not in the TCP/IP model? You can, let me enable the chat. Let me enable the chat, okay. The chat has been enabled. Which of the following is not in TCP/IP model? So we say TCP/IP model has 4 layers. Okay, I'm seeing some people are saying A, some people are saying C, some people are saying E. Okay. All right, can I get a volunteer to just remind us of the layers in TCP, the 4 layers in TCP/IP model? Someone?
In TCP/IP model, we have the application layer.
Okay, application
we have
layer.
The transport, network.
Repeat again from the application layer.
Application layer, the transport layer, the network layer, and that's what, network interface?
Internet layer.
Sorry. Yes.
Internet layer.
Internet layer. Yes.
Network access layer.
Network access.
And network
access layer.
Network access layer.
So referring to this question, which one is not part of them?
A data link.
Session layer.
Session layer is not there.
Data link.
Session layer. Okay, if it was a multi-choice question, also data link would qualify. But remember, we said some reference models also include the link layer, right? The data link layer. So some models have 5 models. If it is a single choice, then you only go with session layer, right? Okay. So which of the following packets is the host of the TCP 3-way handshake?
B is sync. So
sync. B.
It is sync. We said when you're establishing a TCP connection, we said that we send the SYN packet first. Which packet is the second one?
Sync plus acknowledgement.
Yes. SYN plus acknowledgement. What is the third one?
Sync plus acknowledge.
Acknowledgement.
Acknowledgement. If we are closing the termination, if you are closing the connection, we have how many?
Finish.
Fin.
We have how many shakes? There are 4 shakes, right?
There are 4 shakes, yes.
The first one is
finish.
Is finish. The second one is
Acknowledge.
Come again.
Finish.
I can't
Finish acknowledge. Finish acknowledge.
Finish acknowledge. And the third one?
Finish and plus acknowledge.
Finish plus acknowledgement. And then lastly,
Acknowledge.
From the client. Okay, so that brings us to the end of this class. We have looked at the TCP architecture and we have looked at the common network protocols. And I want to thank you for being part of this class, and I will stop the recording from here.